Welcome. This lesson is all about isotopes. If you're joining me right now, what I would like you to do is to please make sure to, first of all, download the guided notes at the bottom of this video. You can print them out and fill in the blanks as you go along. Number two, know that the links in the online document will be active. The links that you'll have is something called the chart of the nucleides over here, a simulation to help you do what's called weighted atomic averages, something called Isotopes Matter, which I'll explain in a minute, my YouTube station. And here's the agenda. We're going to talk about pretty much isotopes. Let's first of all figure out what they are. How do we write them as far as symbols are concerned? Then we're going to say, where do we find these? Chart of the nucleides and a simpler chart called Isotope Matters. And then most importantly is calculating the mass of the isotopes. If you're confused about the last part after you go over it, feel free to bring questions to class. You can always ask questions in class. And I have a simulation over here that will also guide you in figuring out how to do what's called a weighted average, which is the average, the atomic mass that we see on the periodic table. So without further ado, let's go ahead and get started. So first of all, what is an isotope? If you look right here, there are three types of carbon atoms, which looks kind of strange. But the question is, how are they the same and how are they different? Well, any element, any atoms of the same element always has to have the same atomic number and therefore the atomic, which is the number of protons. And so if you look, 6 protons for this carbon atom, 6 protons for this carbon atom, and 6 protons for this carbon atom. The atomic number is always the same. Change the atomic number, change the number of protons, you completely change the element to a different element with different physical and chemical properties. What is different, though, is what else is in the nucleus, the neutrons. This carbon element, or isotope as we call it, has 6 neutrons. This one has 7, and this one has 8. So, isotopes are elements that have the same atomic number. That means these are all carbon, they're all the same, a different atomic mass number. Okay, so different atomic mass. It's kind of like M&Ms. You can have peanut M&Ms and plain M&Ms. They're both M&Ms, they just have different masses. One way to look at it. So that's what they are. Now let's talk about how do we write these. So to be able to write them, one of the things we're going to do, I'm going to try to do this here. So let's use carbon as an example. There's usually a couple different ways we can do this. One of the ways I'm going to show you, let's take it for an example, carbon 12 and carbon 13. One way we can do it is like this, where you put the elemental symbol, a dash, and the atomic mass number in front. So this would be carbon 12. This would be carbon 13. These are 2 isotopes of carbon. When we write them this way, we're assuming that if you have a periodic table in front of you, it's very easy to identify C as carbon. The atomic number is 6 protons. If we know the mass number, which they give us, we can find the number of neutrons by subtracting the atomic number from the atomic mass number. That's one way to write them. And these are also called nucleides as well, just a synonym for isotopes. The other way to write it is where people give us a little bit more information. So they still have the atomic mass number in the upper left-hand corner, and they're kind enough to put the atomic number in the bottom bottom left corner. So that also, so these are 2 ways that you could see symbols for isotopes. That 2 ways that you can see them written. Okay, so we're going to erase that and go on to the next one. So now, once we have these isotopes, and as I'm erasing this, the different isotopes occur differently in nature, and some of them are radioactive, and that property can be used for all kinds of really incredible stuff, which hopefully we may get to later. Okay, so that being the case, let's keep moving. Now, where do we find, how do we keep track of these? Well, there's this amazing thing called the chart of the nucleides, and the periodic table is pretty cool. This has the periodic table on steroids because it has every element that's on the periodic table, but then it has every isotope of every element. And the thing that's kind of amazing, I think, is when you look at this. So for instance, if we go way out, you can kind of scroll out here. So this is kind of like what I call 2.0, but you can move around and see this is huge. I've actually seen this on a wall before, and it like takes up an entire room almost when you actually put the printed version up. So we're going to try and scroll in here a little bit, and you can see it's just like this sea of elements. But the part of this that's kind of amazing is that every element has, like, here's calcium. This has probably 30 or 40 different isotopes, and you can click on each one and get a lot of information for each isotope of the element calcium, which is just overload. So something that's kind of a little bit nicer is this thing called Isotopes Matter. The International Union of Pure and Applied Chemists, otherwise known as IUPAC, puts together. It's it's a little more user friendly. Let me get it here for you. It's a user friendly version of the learning about isotopes. So, for instance, if we were to click on neon, for instance, it just has some really nice information. It has the atomic mass of neon, the atomic number. It has the main isotopes, and you can click on these other things. And the really cool part I like about it is that it gives you information of where these are used in industry, where they're used in medicine, where they're used in research. Why is it that these may be as important as they are? So that's kind of a nice little thing that can tell us why these are so important. Okay, so now the question is, if on the periodic table, okay, the atomic mass is the number of protons and neutrons, and we get these atomic masses on the periodic table that have decimal points, how can you have like 0.5 or 0.3 or 0.2 of a neutron? Well, the answer is you can't. And so what they do is they go to the chart of the nucleides, and they take all of the isotopes, and they say, okay, we're going to take an average of all these isotopes. We'll take all their masses, and we'll take an average. And instead of just adding them up and dividing by the number of isotopes, they do what's called a weighted average, which I'm going to show you here in a minute. What that does is it says, look, if in nature, if there's a higher percentage of one isotope and there's only a tiny percentage of the other isotopes, let's make sure the higher percentage isotope, that mass counts more in the average. And that's called a weighted average. And we'll have some problems with that, but I'm going to give you a ballpark idea of how this is done. So first of all, here are 3 of the several isotopes of neon. Okay, we've got these 3 right here, 20, 21, and 22. Now, this is the relative atomic mass, and these numbers are atomic mass units. It's based on 1/12 of a carbon-12 atom. And so they can find the sort of like what are called the atomic mass units of just these individual isotopes. And you can see that they're very close to what like neon 20 is, like if you round that and so on. And so this is what, these are the 3 main isotopes. Now, instead of seeing this as the word mole fraction, see this as a percentage. Okay. It's saying in nature, by percent abundance, about 0.9048 or 90% of neon found in nature has a mass of, is this neon 20 with this mass? About 0.0027%, 0.27% has a mass of this, okay? And then about 9.25%, so if I move the decimal place over that many times, has a mass of this. So instead of just adding all these up and dividing by 3, it would make sense that if this one contributes much more to the overall mass of neon, if we take a handful of it in nature, it should count for more. So here's how we do that. If you say 0.9048 times this number, this is the number we get. So if this is so it's saying that there's a lot of this, right, and this will contribute to the overall. Then we have this one, right? The 0.0027 times this or 0.27% of this number gets this many grams, and then about 9.25% of this number gets this. So if we were to try and draw this out, right, the way that I did that is these are multiplied together. I'm trying to do this here. Sorry about that. Multiplied together. That's how we got like multiplied like these right here. That's how I got this number do these right here until I got this number, and these right here until I get this number. Now we add all those up. Okay, we add all this up, and guess what? We end up getting 20.13. That's the number that we tend to see on the periodic table. And that's where those decimal points come from. So that's basically a crash course in this wonderful world of isotopes. Now, as I'm erasing this, I mentioned, hey, some of these are kind of important. And if you recall back just a little while ago, we saw something called carbon-14. Turns out that there is a specific percentage of that in all living matter. It also turns out it undergoes this weird thing that we'll find out about later called radioactive decay, which means it starts to kind of go away after a while. So scientists can find things that are really old that used to be alive. They find out the percentage of carbon-14 in it. They compare it to things that are alive. And they can figure out about when they were around, like tens of thousands of years ago and all that, which is kind of cool. So that's a crash course. Don't forget to please do the guided notes. And if you have any questions, do not be afraid to ask.